The last presentation for today, Professor Timur Atabayev, Associated Professor from Nazarbayev University, topic we've already touched upon relating to green hydrogen as part of other topics. Well, actually, I prepared my presentation in Russian as I was asked. My topic today, overview of green hydrogen evolution systems and their applicability in Kazakhstan. So this is the content of my presentation. So I'll give you brief information about hydrogen in general, economic justification of the electrolysis process, storage of hydrogen, photoelectrochemical methods, and how climatic peculiarities of Kazakhstan influence green hydrogen. And in the end, I will talk about the research in the field of green hydrogen that are conducted at Nazarbayev University. So here, general information. This information maybe is known to everyone. So hydrogen is the gas without color and smell, with the density around 90 grams per cubic meter, 90 grams per cubic meter under the 0 Celsius degrees, and hydrogen in industrial scales is used around a century already, so it's quite an element studied well, and it's used in the Haber's process and for hydrogenization of unsaturated fats, so to get dehydrogenized oils. And the Haber's process is when you mix nitrogen and hydrogen in 1:3 ratio. Then this mixture is put into catalytic reactor where you have a catalyst, iron catalyst, and under the appropriate temperature and pressure, this is transferred into, the gas is transferred into ammonia. And when you cool this ammonia, it is then transferred into liquid, and then liquid can be collected. And obviously, there will be some gases that had not reacted that can be using the pump returned to catalyst system, and they can be then again returned to production of ammonia. And production of this unsaturated fats, it's a known process where we have double links, and you use a catalyst for destruction of this double links. And with the hydrogen, the additional atoms of hydrogen allow you to get unsaturated fats. And the hydrogen, as I said, is already been used for more than a century. And the modern methods for the use of hydrogen include also receiving important chemical agents with the high added value. One of the important reactions is the synthesis of methanol. And methanol is a valuable chemical product because it's both precursor and also the solution for producing other chemical agents. But at the same time, it is also a very good fuel, because when the methanol is burned, a very high number of heat is produced, and then the carbon dioxide, which is collected, can be collected again, and after the cyclical reaction, it can be turned into methanol. And first commercial project with the planned annual production of methanol, 110,000 tons per year, is planned to be opened in the second part of the year of 2023 in Anyang city in China. And the project provides for the collection of the CO2 in around 160,000 tons of CO2 from the air. So it will be catching or absorbing the CO2 from the air, then it will be dissolved, and then it will be mixed with hydrogen, and then the process will go on the catalyst. So the methanol, which did not participate in reaction, will go again through the cycle, and as a result, you will get approximately 44,000 tons of methanol, which can be produced on this plant. This 160 tons of CO2 is approximately equal to CO2 emissions equal to 60,000 cars per year. So it equals to removing the 60,000 cars per year. And in the latest years, hydrogen is considered as the fuel for this ethanol installations, and the reason explosion risk element, and developing hydrogen cells without burning processes is in the development stage, but we understand that efficiency level of this fuel cells is not very high, and in the best case it's 60-65%. And moreover, these hydrogen fuel cells, they have high cost just because one of the catalysts that is used there is platinum. So can you assume that you create some fuel cell, but you need a lot of platinum for that? Second important element that we have to take into account is that when we use fuel cells, hydrogen fuel cells, you need to have high quality hydrogen, like 99.9999. Otherwise, the catalyst will be poisoned. So there is such a process which we call when we get the hydrate of metal in the process, and this is very bad for the metal. What can we do in order to use hydrogen in commercial means? We need to solve several technological tasks. First, for the incineration burning process, we need to use a mixture of gases, and the most optimal is hydrogen plus methane. But you also understand that methane is not always available everywhere. That's why we can consider some other gases that will significantly dissolve hydrogen. If you want to use for this fuel cells, if you want to use it for fuel cell, for example, in the second case with the use of fuel cells, they can be used for cars, for planes, like Airbus, for example, is considering now the potential to use this hydrogen for the flights, so that then these plane flights will become carbon neutral. But we need to increase the coefficient of efficiency, and in order to achieve that level of efficiency, we need to somehow treat this hydrogen to make it cleaner, and we need to find some stable catalyzers for that. And if we go to economic justification of that, of the whole catalysis process, in the classic electrolysis, when you put two electrodes into water and then current is going through them, in order to get 1 cubic meter of hydrogen, you need around 5 to 6 kilowatt hours of electricity. But we need to take into account additional losses for the cleaning of the hydrogen, because there are some steam involved. There's some steam involved as well, and cooling is required. And the cost for the production of green hydrogen is around from $2.5 to $6.8 per 1 kilogram. And the cost here depends much on the cost of electricity in the countries. In Kazakhstan, I made my calculations. And what is important here, that the cost shown here is the cost for the consumer. If you will be using it in industrial scales, the cost will be higher. It will be around $3 to $4 per 1 kilogram. If you are aware with the Department of Energy of the United States, it has put a target for itself to reduce the hydrogen cost down to $2 per kilogram per 2025, and I'm sure they will be able to achieve that target, because as of today we can actually offer similar prices already. maybe by the end of the next year, we will definitely be able to achieve that. And the next target is approximately $1 by 2030. And with the price of $1 and lower, the hydrogen fuel can be competitive with other fuel sources or electricity sources in the United States. And it's important to know that it's United States, because if you compare it to Kazakhstan, it will be completely different prices. And why hydrogen? The heat of burning of hydrogen, when you burn 1 kilogram of hydrogen, you have around 141 megajoules of energy. And if you compare it with timber or with coal, for example, andesite, then it's around 31 megajoules. And if we consider that our coal is not always the best, approximately we need to burn around 5 kilograms of coal to get similar amount of energy like with 1 kilogram of hydrogen. So, as for the economic rationale, you see, and the lower the price for hydrogen is, the better it is for us. And then let's move to the next question. Another important thing to mention is the storage of hydrogen, which is also a difficult technological task that should be solved for effective hydrogen energy. Storing hydrogen in liquid and gaseous conditions is very expensive, and it requires a lot of capital expenses. If you want to, for example, pump 1 gallon, one big tank of hydrogen, if you calculate how much hydrogen is there, it's 40 grams of hydrogen per 1 liter of gas in your balloon. And if you cool this hydrogen up, yes, it will move into liquid form, and here you will have higher number of hydrogen, approximately 71 gram, 2 times more. But you have to take into account that you will have to cool it down to 21 Kelvin, which is technologically very difficult. And if you look at other methods like materials-based storage, is storing hydrogen in the form of materials like there are different hydrates, complex hydrates, and chemical storages, different sorbents, very porous sorbents where hydrogen can be stored. If we compare the effectiveness of storing hydrogen in such materials, they do not cost much cheaper for you, but in terms of quantity, they cannot really compete with clear water, because water gives you around 111 grams per liter, and here you have a lot of hydrates which are synthesized all the time from 100 to 150, so the difference is not very big. So the most optimum storage approach, according to the weighted potential, is clean water.
The localized hydrogen, production of hydrogen on site and for immediate use. If you try to inject it somewhere or cool it, you will need additional energy, which is not good, because hydrogen, as you know, can easily leak through different materials. And over time, especially if you inject into balloons, the scope of hydrogen will reduce because it will go through the walls. Now let's talk about photoelectrochemical method of receiving hydrogen. These are the cells that are currently can be used as a photovoltaic panel. It's actually similar on the principle, how it works, but it is different from the solar panel because you have 2 photoelectrodes and they are in the electrolyte connected to each other. On one of them, there is a semiconductor that generates the light, and it interacts with water, emits oxygen, electrons go on top and get to the next electrode, and they restore hydrogen. If you create this type of cell, you can quite efficiently collect hydrogen and oxygen in quite good clearance, purity. Here is how the laboratory cell looks like. There are two cells, and here is a membrane that actually can conduct the protons, H+, and the protons, when they go through membrane, they restore hydrogen here. If you just divide them, you'll have a hydrogen and oxygen of high purity. Oxygen you can release, and you can use the hydrogen for your needs. For stable work of this cell, semiconductor anode should meet the following requirements. It's clear that a photoanode has many limitations. Your photoanode should be quite stable. According to the energy department requirements, it should work at least 10,000 hours without degradation. If it works this amount, you can replace it. It should also absorb a wide range of solar spectrum, which is not always possible because the rate of reaction can be different. The rate of generation and the rate of division in the photoanode should be higher than the rate of recombination of electrons and hole pairs. Otherwise, if it's not generated, there will be no reaction. And the last requirement is, of course, the economics. Your material should be quite cheap for generation and for the use. Here you can see different types of cheap materials that were offered recently. And you can see their potential about splitting oxygen and hydrogen. If the width of your zone is between these two potentials, then it actually matches for splitting hydrogen. Match this can be helium phosphide, silicon carbide, tantalum oxynitride. There are only a few materials, and if you continue to see their stability, you will have only one or two materials. One of them, dioxide of titanium, and it can absorb only ultraviolet rays. The rest of the spectrum, you know that in solar spectra, ultraviolet is 3 to 5%. The rest is the this light that we see, or infrared. And considering all this, our group has prepared a precursor that consists of the nanoparticles of titanium dioxide, and we injected a material, restored graphene oxide. What we were able to achieve, due to the fact that we have these particles, we had a stable photo flow and materials resistant to corrosion. So that we used such materials, we had a rate of recombination, and these couples, they participate in reaction. That's why we receive hydrogen and oxygen. And the third, the fact that we use this double material, the currency density increased, and that reduced the energy use for receiving green hydrogen. Here is one of the pictures. There are actually many of them, but here you can see this is the conducting glass. It's about 1 micron size of CO2 particles. That also includes restored graphene oxide. And if you compare the density, and you will see that it increased twice. Density increases of the photocurrency, photo flow, and it means that you need to provide twice as less voltage because the film generates the electrical current. And you give less voltage, less additional current to produce hydrogen. This work was published in February, on February 8th, 2022, with our PhD students, with our master degree and bachelor degree students. That was published on February 8th. And on February 10th, our paper was selected as one of the best among the submitted papers. That was published in an international news forum that publishes the technological results of such projects. And these materials can be used not only for electric catalytic production of hydrogen, but also can be used for solar panels because they increase the speed of transition to the third generation of solar panels. Let me get to the climate diagrams now. We have analyzed climate diagrams of 3 cities in Kazakhstan. This is Astana. We got the data from Meteo Blue. They analyze average data about number of sunny days and windy days in Kazakhstan and all over the world. In Kazakhstan, we have selected 3 cities, Astana, Almaty, and Atyrau. If you see well, you will see that we have a minimum number of sunny days. Even in Almaty, not that many sunny days. Same in Atyrau. But if we look at this wind velocity, we know that there are stable velocities from 10 to 20 meters per second. It's almost every day. In all the cases, we have these velocities. Wind is always there. What does it give us? It gives us understanding how we can use our photocatalytic films because they work only with the solar insulation. Due to the lack of sunny days, we decided to use a hybrid installation. This is also a cell, but the electron flow was moved to another reservoir. In one place, there is only oxygen, and in that reservoir, only hydrogen is generated. Yes, I am finishing. If you have sun, then that's excellent. Your system generates hydrogen and oxygen. If there is no sun, it's okay, because this catalytic coating is quite stable. You can use a small voltage that will be provided on the basis of renewable sources. You can use, for example, wind-based electricity. If there is no sun, okay, you can use renewable energy. Or if there is no renewable, you can use batteries. Batteries will accumulate the energy, and you will have a stable source for producing green hydrogen. And the last slide, the research on hydrogen held in Nazarbayev University. We are trying to do the design of these installations, and we try to improve the efficiency of such cells. We plan to use renewable energy in Nazarbayev University Technopark. Here you can see we have solar panels and we have wind turbines for creating a first pilot prototype. And if we are successful, we can scale it up and commercialize. The project of using hydrogen fuel, we now try to use it for heating of small buildings, and in future there is an additional project of converting hydrogen into a product for chemical production. Remember this scheme, you can convert hydrogen into methanol. You can store and transport it to longer distances, and it's much easier than with hydrogen. And I would like to thank our grant applicants. We have 2 grants from Nazarbayev University and 1 grant from the Ministry of Science and Education. The ministry is very much interested in this research and provide grants to us. This is it. If you have any questions, I'll be happy to answer. Thank you. Sorry that we have lagged behind. Now all the speakers are here. You can ask questions. There is a general question. You said that the green hydrogen is a hydrogen that is generated out of water. And considering the export of green hydrogen from Kazakhstan, and considering that we generate it from water, isn't it a conflict here that we have a shortage of water and we actually will export water and there is a shortage of water? What do you think about it? Very good question. Yes, I've been thinking about it, and you are right. We actually have kind of like a hidden experts of water. But what's the difference of our project with the project that the government of Kazakhstan is going to sign with an Australian and European companies about exports of green hydrogen? Our project actually means that we will extract water from air. There are some processes that you can get the humidity from air, and the air exchange happens all the time from different countries. So there will be humidity in air all the time. It doesn't mean that we'll extract water from the water reservoirs. Thank you. Other questions? Maybe there are questions online. I would like to thank.
In this conference, this online, practically the number of people will not change.
You said that you will extract water from air, and then it's not quite clear why we will hold it here in Kazakhstan. The average humidity of air is lower than in Europe. Then maybe you can generate it there in Europe, not to transport it. I agree with you. It's simpler to do it at their territory, but there is also important the issue of technological development of Kazakhstan. You can produce in Kazakhstan and you sell it from Kazakhstan. And for internal use, you can also produce methanol. And if we can mix it with a small amount of nitrogen, we can even develop electricity. And that's better than burning coal. Thank you. Let me comment about extracting water from air. As far as I know, we are fighting droughts by artificially causing rain. So our objective is to increase humidity in the air to have more precipitation. We know there were big droughts in Mangostau and in the north of Kazakhstan. If you use this method, maybe they will have some adversarial impact for the climate. because we already have dry air. Well, that's a more complicated question, and that's subject to discussion. I agree that it may cause some local dehydration of air, but on average, in general, that's maybe the question for climate specialists, how air is moved around the world. Actually, I haven't studied this. The more humid air can move to arid areas. There are pilot installations of getting water from air, and even in the Sahara Desert, the air humidity was very low. Still, they were able to extract quite a large amount of water from the air. And since the air is moving all the time, it's won't be a big risk locally, I think. I agree that we can also select a site where people don't live. Yes, thank you very much. And there is one more way to use hydrogen that is generated here in Kazakhstan and use it efficiently at the space shuttle, for example, place. And this will be a environmentally clean fuel for space rockets. And it's not necessarily even to sell it to France, for example. Any other questions? Thank you very much. We have used up all the time, and I thank all the participants.
And also, thank you very much for all our speakers.